All right, everybody, great to have you back. This is Mr. Mays. I've got my little 2-month-old strapped to my stomach right now, just so you have a visual. So he's going to be helping us out. You'll hear a couple of moans and groans. That's not my stomach or me, it's my little boy. But we're super excited to be working with you today. And what we're going to be messing around with today is we're going to talk a little bit about the kinds of things that you need in order to understand types of data. And we're going to look into categorical data and quantitative data and the kinds of graphs that signal these types of data. So, big things to start out with. You must know what an individual is versus what a variable is. Pardon my handwriting. Now, individual, we're not talking about man versus wild or some existential crisis of self. Individual, in effect, are just objects or things, either or. That's a T, that are described by variables. Okay, so for example, if I'm looking at a survey, I know we had some diagrams before of different kinds of graphs, and I'm looking at, a pie graph and it's about, number of deaths per year. My individual in that case would be people, right? Because we're looking at the deaths of people, not of dogs or not of cats or, lycanthropes, which I think is actually werewolves, which don't exist. So there we go. But the individual or individuals are the things about which our data concerns itself, right? Versus the variables themselves, right? Those are the things that we are measuring in our individual. So the things being measured about the individual. So again, fairly simple concepts, but really important to know this vocabulary. So when we talk about various kinds of data sets, you feel easy breezy, beautiful cover girl. Okay. Individual and variables, easy money. Okay. And once again, and this is super important to remember, data is just numbers in context. Remember, that's the C from CSOX, which you'll see next set of videos. We'll be messing a lot with CSOX, but in this particular case, actually, let me erase that border. What I really want to do is highlight that C. The first C in CSOX is context, and that's super important. That's the thing that makes the data valuable or understandable in some way. Okay, moving ever forward. We've got our background. One thing I really want to sink home is kind of how this works. So the example I gave in class was you have a latte, you have a mocha, and you have an iced coffee, and you're chilling, you're living your life, you're having a dream or whatever, and you're measuring temperature and sugar content maybe of these drinks. So I'm going to throw some data points in there. We'll say hot, cold, and we'll say 70 grams, 150 grams, 60 grams, okay? So these are the measurements, and what you would say about this data, right, is probably something like this. You would say the individual here, and I asked the majority of the class this, and everyone was pretty clear that the individual here was just coffee, right? We are measuring or trying to determine things about coffee. We have done a study concerning coffee. Now, the question, on the other hand, of the variables here, the variables concerning are temperature and sugar content. Right? So altogether, we have two variables. All right, and that's super important. If you remember in class also, we went into more detail on this, but we determined one important thing about variables is sometimes we make a huge mistake and we think that the categories of the variable, especially for categorical data, which we talk about in a moment in this video, but we start to think that these are three different variables, right? Like hot or cold, but they're not. They're all just one variable known as temperature, right? And same thing over here. We start to think that these quantitative variables, again, we talk more about in a second in this video, number variables, 70, 150, and 60 for sugar content, we start to think those are 3 variables, but they're not. They're all 1 variable known as sugar content. All right, I think I've done a great job of destroying this beautiful little table I've made, so let's move on. Okay, so we understand this stuff pretty well right now. And the last thing I want to toss your way is this idea that distribution, because we use that word a lot, distribution tells us what values a variable takes and how often it takes them. So if I look up here, distribution tells me what values a variable takes. Well, my variable is temperature, so what are the values it takes? Either hot or cold, right? Oh, actually, let me use my fancy highlighter. Hot or cold. Oh, no, that's 2 hots, hot or cold. And then it tells me how often it takes them. So in this case, 2 hot and 1 cold, right? And that's our distribution, is hot, hot, cold, right? And then our distribution, of course, for sugar content is 70 grams, 150 grams, and 60 grams. That's the distribution. Okay, now I've really ruined that graph, so I feel like we've done our work here. Okay, we'll go to red, if it'll let me. There we go, perfect. So we know what distributions are too. All right, let's move forward. Now we gotta roll into categorical versus quantitative data. So, categorical data. Okay, categorical data and quantitative data. When we are looking at categorical data, let me do this in blue, these are going to be groups that cannot, I say cannot, be worked with through algebra. Now, in class, you might remember me being like, this is really important. They can't be worked with through algebra. And you're probably thinking, well, Mr. Mays, why don't you just say anything that's not numerical? But we talked about one of the weird examples of categorical data. Well, let's start with some of the obvious ones, right? Color, for example, of a car. That would be considered categorical data, right? Another commonly used categorical data point might be shape. Shape of something. Anything, again, that's non-numerical for the most part. However, there are some that are numerical, but because we can't use algebra to do anything sensible with them, they're considered categorical. So a good example of that is zip code, right? 22101, etc. Zip code. Okay, and the reason that that one counts as categorical and not numerical is you can't really subtract zip codes. It doesn't do anything, right? So 23187. So these are 2 different zip codes. Subtracting those would do nothing. Averaging them, right? If you added these together and divided by 2, that wouldn't do anything. That would mean nothing, right? And so for that reason, it's categorical data. And as we saw in the activity later, you can actually take things like age, which are normally not categorical data, and if you turn it into the right bin and you do like 18 to 35, right? And you use that in a way where you're making like bar graphs, you're treating a normally quantitative data point, age, right? And we'll talk about that in a second, as if it's a categorical data point. And vice versa, you're using a bar graph to do something that it normally doesn't do. And we'll talk about that in a moment, but these are some sneak peeks. Okay, the big takeaway for now, though, should be that even something like zip code is categorical, and you should feel pretty comfortable with the idea of what a categorical variable is, right? It's just something that you can't do algebraic work with. And most importantly, it's something that is normally non-numerical, right? Okay, and really quickly, I'm going to show you the kinds of graphs that we do with that. I'm just going to briefly show. It's a bar graph. Excuse me, a segmented bar graph. A side-by-side bar graph, lots of bar graphs. a mosaic plot, and a pie chart. Okay, now really quickly, I'm going to go through each of these. You should feel fairly comfortable. You can also look these up and get more of a comfortable feel for them. But here are the big takeaways. Starting with a bar graph, you've seen probably a million of these in your life. I'm going to draw a cute one here. Bar graphs are separate. They are not touching each other. Okay, your categorical variable goes here on the x-axis, and then the y-axis is frequency. For the cases of this course, even though it is technically a dependent variable, your y-axis, we don't count frequency as a variable for the AP exam. Okay, so we have a categorical variable on the x-axis of some sort, right? Bar graphs are always going to be running categorically for the most part. So that's a bar graph. Another example is a segmented bar graph, which we covered in class. Segmented bar graph is just like a regular bar graph, but you have another variable that you're covering by cutting up the bar. So for example, I'm going to use gender a few times in this video just because it's easy to talk about. This could be one graph, and then I do a new version of that graph where I then separate it into, let's say yellow is male, and then the blue bottom, which I'm going to make down here, good job, buddy, is female. You can hear my son there. Perfect. So same thing as a bar graph, but you just add one extra categorical variable, in this case, gender, and you do that by separating out each bar into, well, this amount of it was male and this amount of it was female. Beautiful, and that's segmented bar graph. Now I'm going to do an arrow down, and we're going to roll with side-by-side bar graphs. And again, I'm going to use gender because it's pretty easy here. Same bar graph idea, same categorical variable on the x-axis. But then instead of that normal bar graph, we have a side-by-side bar graph. Now we still have the gap between these two, but in this case we would do like this, male, female, male, female. And normally, actually, I'll use the highlighter to clarify this. The male would be one color, and then the female one would be another color, right? So again, same idea. They accomplish very similar things, the segmented bar graph and the side-by-side bar graph. It all comes down to whether people feel like that is visualizing the data well. And again, that is, in this case, we are measuring two variables, whatever is going on this x-axis and whatever is going on between the two bars. Now we have the mosaic plot. The mosaic plot arguably is a little too crowded. People know that's my position on it. It's one where you basically have an entire square. And just like a segmented bar graph, I'm going to do the same thing. And you might remember this example from class. I did like people who think AP Statistics is the best AP class for math, and people who think AP Calculus is the best AP class for math. But I'm just going to give this sort of breakdown. You're going to have, once again, two main variables being measured, but there is a third one at play. So let's take a look at how that rolls. Now these are coming off the AP exam soon, but for our purposes, they may show up, so we're going to roll with it. Again, we still have frequency on the y-axis, but again, we do not count that as a variable. Then we have a categorical variable on the bottom. Let's say, for example, this was students and teachers, I believe in the example I gave in class. Okay, and then we have this breakdown where we would do, right, like blue is AP Stats, and then red was AP Calc. Okay, and as you can see from this breakdown, we have the different gradations of people that think AP Calc is the most important versus the people that think that AP Stats are most important, who are correct. But then we also have this line here going across because we go the full breadth. So this goes to 100%, the frequency does, but so does our line on the bottom. And what that would be is how many teachers to how many students. So the wider the student side is, the more students I must have interviewed. And the wider the teacher side is, the more teachers I must have interviewed. So based on these metrics, if let's say I did 100 people total, it was likely students were, I mean, this looks like pretty close to 60, and then teachers would be 40, right? Because we have a little more going for the students than the teachers. So we have the same thing going on as we had over here with the segmented bar graph, but we add this element of the sort of the width, the categorical variable going from left to right, is making up its own sort of quantitative measure, right? The number of people in that sample. But the downside is it gets very crowded. And the last one, the pie chart, this will take 2 seconds to draw. You have a circle, and then each slice of the pie might represent a different thing being measured. We know this. It normally measures one variable in general. And then there are frequencies, which again, we don't count. Okay, and those are all metrics for categorical data. So when you see any of these, it should be sitting in your head in terms of this new lingo for stats that I am messing with categorical variables because I saw one of these types of visualizations. Beautiful. All right, let's take this quantitative data. Let's bring it with us. We are ready to roll. Ooh. Going past everything else, all the way down. Actually, we'll roll. And now we say, well, what do quantitative data points look like? And I got you covered. Now, the quantitative data section that I'm going to go through with you today, we're going to do a bit of a cursory look through, and then we're going to do a lot more when we move into next session's videos and also classwork. But for now, here are the things you should know, because this is big for the upcoming mini quiz. Okay, quantitative data is numerical data. Not only numerical data, but as we know, numerical data that you can do algebra with. And actually, I'll say sensible algebra. Okay, numerical data that you can do sensible algebra with. What do I mean? Well, some good ones normally are age, normally, right? Weight, height. These are all good examples of quantitative data, okay? Before I forget, and I almost forgot to do this for categorical, but I'll do it in just a moment. There are two subcategories for quantitative data. I do want them sitting in your head. We may not use them immediately, but I just want you to know these terminologies. There are discrete categorical variables, and there are continuous. Continuous categorical variables are ones where you can have in between values, 1, 1.5, 1.75. So again, weight is like that, height is like that. Normally age is also like that, although a lot of times people round age up and they treat it as discrete. And discrete, on the other hand, is when you can only have sort of separate numbers. And what I mean by that is you can't have a value between these two numbers. So people are a great example, like number of people is a great example of something that you can't have an in-between. You can't have 1.5 people, right? Or you can, but it's illegal. Haha, slap my thigh. Okay, so that's a difference. Sometimes we take continuous variables, right? Like age, and we make them discrete because we're like, oh, I'm not gonna count you being 37.5 years old in my survey. I'm only going to treat it as 37 or 38. And that's an example of how this course will work a lot. We sometimes manipulate some variables to behave certain ways because of different contexts. And that's why we're talking about context so much. So keep that swimming around in your head. Okay, side note, I'm going to do a huge backtrack real quick. So zoom back to where we were messing around with categorical data right here. And really quickly, I want to go over the two kinds of categorical data. We have ordinal and nominal. And this will take 2 seconds. But ordinal categorical data is stuff like, we went over this in class, like gold medal, silver medal, and bronze medal, right? If you win the Olympics, you get a gold medal. Second place is silver. Third is bronze. That's ordinal, coming from order, right? Meaning there's a best, a second best, and a worst. Now, you still can't do math with it, right? There's no such thing as a gold medal minus a silver medal, so it can't be quantitative, but they are ranked. So categorical data that's ranked but not able to do math with, or that you cannot do math with, is ordinal. Nominal is just all the rest of the categorical data. So like car color, for example, is a great example of nominal categorical data because it's just like red, blue, brown, green, whatever. There's no ranking. Okay. Thank you for taking that sidebar with me. Well, to get our heads back in quantitative data land, we're talking about quantitative data, all numbers, numbers that you can do algebra with, and like I said, there are discrete ones and continuous ones. Now let's take a look at the kinds of graphs that we do with quantitative data. This is super important for your upcoming mini quiz. We have the dot plot, the box plot, the histogram, and of course the stem plot. All right, let's rock and roll. Dot plot, mad easy. We have our frequency on the y-axis, and then we have a categorical data of some kind that we're mapping out here, and we map it out. Remember that always with categorical data, we have to include all of the separate numbers to create that data. So even if my dot plot doesn't have anything, let's say this is 1, 2, 3, 4, 5, 6. Let's say I don't have anything under 2, I still have to include the 2. Do not ever skip x-axis values just because you don't have data there. Why? It messes with the view of the curve. Okay? Dot plots are good for a lot of things, but things that you should be aware of that they're good at, you can see whether something is approximately normal with a dot plot. Why? Because you can see how it shows up on the curve, and we can see if there's one hump. You can also see, by extension, modality. What do I mean by that? Well, you can tell if it is unimodal or bimodal or multimodal. And this should be kicking back to the first day's notes, but we'll go into even more detail on this next time. But as you can see, this graph here is unimodal. Okay, and that should make some good sense, right? So we have this graph. Let me erase actually the part where I wrote cat for categorical data. And you can see that these are the kind of the tenets of dot plots. The frequency is how many dots we see on the particular graph. We can make something of a curve with it. We always use quantitative data for the x-axis or quantitative values. And the things that are really good to see for dot plots are mode and the normal curveness of our graph. Or if it's not normal, we will know that. Okay, box plot. Box plot's a little interesting. We go into a lot more detail next time, but here's what you need to know. One, our box plot is not using means, which is rare. It is using medians. We have a median here at what's known as quartile 2. And we should know the median is the very center of our data. And we should know this from the last video. So I'm just going to use this jargon really quickly. You should understand it from last time. This, quartile 1 and quartile 3 are really cool. Quartile 1 is the median of the left half of our data. So the middle number of this half of our data. Versus on the right, quartile 3 is the median of the right half of our data. Now, one thing you will note about a box plot, you cannot see modality with a box plot because none of the data is showing means, so we don't see averages. In this case also, we do not have situations where the distribution is right in front of us. We're just seeing distances between the minimum, which is the far left of the box plot, the maximum, which is the far right, and the different medians, the quartile 2, which is the median for the whole thing, quartile 1, which is the median for the left half of the data, and quartile 3, which is the median for the right half of the data. So we can't see modality, which means we cannot see if it is unimodal, bimodal, or multimodal. And further, I went in the reverse order there for that, my bad. But also we cannot tell if it is a normal curve from a box plot. And that is super important. I would highly recommend writing those in your notes and getting your head around those ideas in your notes. And if you have any questions about why that's the case, if this doesn't make sense from the video, come find me. You know where to find me and when to find me, and I got you covered. Okay? Excuse me, big burp. Okay. And our last two, the histogram, again, frequency on the y-axis. On the x-axis, we have our data. For the histogram, we must have the bars touching. You must always have the bars touching in a histogram. Do not ever make a histogram without the bars touching. They take points off for that. You'll have your quantitative variable here. And the important thing to note about this variable for a histogram is you will have what are called bins. Those bins should pick up where the last one left off and should go through to show you all of the values going through. So if I were doing age groups for my histogram, my bins might be 0 to 15. And that would be my first bin for the first bar. But then if that's the case, my second bar would have to be 16 to 30, not 15 to 30, 16 to 30. And then again, 31 to 45. Notice that my bins are all equally sized. Always make your bins equally sized, right? And always make sure they are touching one another. Okay? And the histogram is phenomenal. Again, you can see if something is approximately normal. You can also see if something is like roughly uniform, same deal. You can see that with the dot plot as well. And you can also see modality, right? This is part of why we love the histogram. The histogram, as the kids say, rolls deep. Okay. And then we have the stem plot. Let's take that over here. Thank you for bearing with these lovely messy notes. You can see, but look how pretty it all is. I'm just kidding. It's the colors that are really deceptive. Then we have a stem plot. Okay, we'll get really clean and clear on the stem plot. Here is a stem plot. Okay, there is the stem side and there is the leaf side. I'm going to pick some values. Okay, let's say 15, 26, 27, 27. And let's say 35. Okay. Now, if we go through, well, and actually, let me also do 35, 35, 36. Okay. If we go through and go to label this stem and leaf plot, it would look something like this. Just like that. Okay. And we would have to put a key here, and we would say key, colon, 1, line 5, equals 15, and let's say these are years old. So 15 years. And that would be our key. You must always, always, always make a key for your stem and leaf plot. Imperative to have a key for the stem and leaf plot. It must look like this, where you denote both what the value means and what it measures, in this case, years. The other thing you will note is that none of our stem values that are next to each other, none of our leaf values that are next to each other have commas. We do not put commas there. Sometimes I put commas there because I'm being careless, and you shouldn't follow my advice on that, because even though it's like normally considered okay to put commas there, for the AP exam, not putting a comma there shows them that you understand that you only ever put single digits in the leaf column. Only ever put single digits. And that's a good guiding point for you for when we have weird kinds of stem and leaf plots. Like when you have decimals, for example, like 31.5, 37.6, the things after the decimal will go in the leaf side. The other thing to remember is, just like with the histogram bins where you can't skip any, or the dot plot bins where you can't, well, I guess they're not bins, but the dot plot markers where you can't skip any, and the same thing goes for box plot, you cannot skip a number. So let's say I were making a stem and leaf plot, and I only had like 11, 21, and 44. I still have to do 1, 2, 3, 4, and my data would look like this. And there would be no number here. We don't put a 0. We would only put a 0 if 30 were one of my values, right? Because then it would be 3, 0, but 30 is not. So I just leave this place blank. You will also notice that upon looking at this distribution that I've created up here for this stem plot and leaf plot, it is very easy to see if something is normal from a stem and leaf plot, and if there are modes, modality, right? So really quickly, if I had a stem and leaf plot, and I saw numbers like this, and let me think, 2, 4, 5, 6, 2, 4, 5, 0. We would call this, and this is super important to recognize, this right here would be considered a bimodal distribution. And one reason I showed you this one is because I think a lot of people think that whichever line goes up to the top counts as a mode. So we'd be like, isn't it trimodal/multimodal? But no, this counts as all one mode because we have one peak here for this data. Okay, this is a different kind of mode than you're used to. You're used to the mode just being the number that shows up the most. But in this case, we have a mode that sits in the 20s and 30s. And then we also have a mode that sits in the 50s. It's where our peaks of distribution sit. All right, now you should feel, let me just go back through. You should feel sensible about how stem and leaf plots work. Don't use commas, do create a key. You should also feel really solid about the other kinds of quantitative data visualization, sorry about that. Like the histogram. Always make sure that the bars touch, make sure your bins are equidistant and they are good quality bins and that everything is touching. Box plots, make sure you're working with medians. Be aware box plots are not good for checking normal curve or approximate normality. They're terrible for modality too. They can't tell you if something is unimodal, bimodal, or multimodal. On the other hand, dot plots and stem plots do a phenomenal job of that, and we can see a dot plot is just a series of dots placed over quantitative variables with a frequency on the y-axis. We talked about the fact that there are two main kinds of quantitative data: discrete and continuous. Continuous, where there are values in between the whole numbers, and discrete, where there are really just chunked whole numbers and you can't go in between, like entire people, entire animals, things of that nature. We then went over the kinds of categorical data, or I guess in reverse, we went over the categorical data. Things like the mosaic plot, where we have these distributions and we measure multiple variables, many, all at once, right? And then we have examples like the pie chart, which are very simple, one variable measured. We talked about the fact that variables are not the same as the categories that make them up, so be sure to be checking that you're actually calling a variable. And we talked about the fact that we don't use frequency as a variable. We also saw gender being split up in a side-by-side bar graph for an extra variable. Normally we have two variables in a side-by-side bar graph, both the variable measured by the two side-by-side bars that are clustered and the variable being measured on the x-axis. Then we also saw a segmented bar graph with the same idea, but where the second variable is split up between two segments in one single bar. And then the regular old bar graph, which measures normally one categorical variable. And we took in mind the fact that these are all categorical visualizations as opposed to quantitative ones, and that the two main kinds of categorical visualizations are ordinal and nominal. Okay, and then we went over distributions. We went over what variables truly are. We understood that data are numbers in context, and that's the context part of CSOCs that you should feel comfortable with. And we went over what individuals versus variables are in general. You have been heroic. I know that has been a long video. I hope that gives you clarity. Please come find me if any part of this beautiful, messy show has not made any sense. I adore you. You have got this. And this is Mr. Mays signing off.